Let's start with the antiderivatives that are inverse trigonometric functions. We know that the derivative of the arcsine x is 1 over square root of 1 minus x to the power of 2. We get that the antiderivative of 1 over square root of 1 minus x to the power of 2 is arcsine of x plus c. We know that the dx of the arctangent x is 1 over 1 plus x to the power of 2. We get that the integral of 1 over 1 plus x to the power of 2 dx equals to the arctangent x plus c. We also know that we get that the integral of 1 over x times the square root of x to the power of 2 minus 1 dx is the arcsecant x plus c. We already noticed that the derivative of the arcsine of x is 1 over square root of 1 minus x to the power of 2. But also, the derivative of the arccosine x is almost the same. It is negative 1 over square root of 1 minus x to the power of 2. It means that the antiderivative of 1 over square root of 1 minus x to the power of 2 has two answers. Okay, so the first one is the arcsine of x plus c, and the second one is the negative arccosine of x plus c. Just because of general agreement, I would say that if you look at the books and the chart, you're usually going to see the arcsine of x plus c. There are more cases like this. The integral of 1 over x to the power of 2 plus 1 dx, it's not only arctangent of x plus c, it's also negative of the arccotangent of x plus c, and also the same story with the antiderivative of 1 over x times square root of x to the power of 2 minus 1. It is arcsecant of x plus c, but also, and you don't see this often, negative of the arccosecant of x plus c. d dx of the inverse to the sine hyperbolic x is 1 over square root of 1 plus x to the power of 2. This implies that the integral of dx over the square root of x to the power of 2 plus 1 equals to the inverse of the sine hyperbolic x plus c. From this, we get the following integral. The integral of dx over the square root of x to the power of 2 minus 1 is the inverse cosine hyperbolic x plus c, but this is true only when x is more than 1. If you notice, if x is less than 1, then you will get negative number under the square root, which is definitely not allowed. Also, x cannot be strictly 1, because you cannot substitute 1 to the power of 2 minus 1, you will get 0, and the square root of 0 is 0, and you will get 0 in the denominator. And now we have another surprise. The derivative of the inverse tangent hyperbolic x and the derivative of the inverse cotangent hyperbolic x is 1 over 1 minus x to the power of 2. It means that the integral of this one is supposed to be equal to what? The first one or the second one? And here's another surprise. It all depends on the value of the x. If x in absolute value is less than 1, then this is the inverse tangent hyperbolic x plus c. And if x is more than 1, then this is the inverse of the cotangent hyperbolic x plus c. When x is 1, this is not defined because, again, there is a 0 in the denominator. The restrictions for those values of x's are because of the domains of the two functions. Now let's look at the antiderivative of those two forms. the integral of dx over square root of 1 minus x to the power of 2 is the inverse of the sine x plus c. And the integral of dx over square root of x to the power of 2 plus 1 is the inverse of the sine hyperbolic x plus c. It's really very confusing. The integral of dx over square root of x to the power of 2 minus 1 is the inverse of the cosine hyperbolic x plus c, and this is true again only when x is greater than 1. What about the antiderivatives of 1 over 1 plus or minus x to the power of 2? The integral of dx over 1 plus x to the power of 2 equals to the arctangent x plus c. But this guy, I recall, it's about the inverse hyperbolic functions. It is the inverse tangent hyperbolic x plus c when x in absolute value is less than 1, and it is the inverse hyperbolic cotangent x plus c when x in absolute value is more than 1. Now let's see some antiderivatives of hyperbolic functions. From here we easily get that the integral of cosine hyperbolic x dx is sine hyperbolic x plus c. From here, the integral of sine hyperbolic x dx equals to cosine hyperbolic x plus c. Because of this, we get that the integral of the secant hyperbolic to the power of 2 of x dx equals tangent hyperbolic x plus c. From here, we get that the integral of the cosecant hyperbolic x to the power of 2 dx is negative cotangent hyperbolic x plus c. From here, we get that the integral of the secant hyperbolic x times tangent hyperbolic x dx equals to negative secant hyperbolic x plus c. And from here, we get that the integral of cosecant hyperbolic x times cotangent hyperbolic x dx is negative cosecant hyperbolic x plus c. This is very similar to the trigonometric integrals, but you have to be very careful with the pluses and the minuses, because there is a really big difference with the minuses and the pluses here.